Okay. Yeah. Okay, let's start. So far in this course we have seen, and hopefully you guys have learned how to design op-amps. So in the last few classes of the course, we'll briefly look at some circuits that are made using op-amps, which are practically useful, and you'll see in all electronic systems. Can you close it? And yeah, I mean all these circuits are made with op-amps with negative feedback. So first, before going into it, a brief motivation for those circuits goes as follows. So if you take any electronic system, it needs to be powered by a DC source, right? Let's say you take your mobile phone, for example. It has whole number of chips, and let us say it has a digital processor, which typically digital chips are made at the cutting edge technology. So let's say it's running at 0.6 or 0.8 volts. Let's say you have an RFIC that requires a supply of say 1.2 volts or 1 volt. You might have some baseband analog portions running at a slightly higher voltage, say 1.5 or 1.8 volts, and you might also have display drivers, so that will require slightly higher, I don't know, let's say 2.5 volt or something. So you need to generate all these supply voltages so that your circuits work fine. So in for your cell phone, who provides all this? I mean, who powers your cell phone finally? What is providing the power to your cell phone? Battery, lithium-ion battery. So the lithium-ion battery, what is the nominal voltage it provides? No idea. Okay, so when it's fully charged, it turns out it's about 4.5 volt. But of course, the battery is not fully charged. It starts discharging. Of course, if you let it stand by, it will discharge slower. But if you keep watching Instagram reels throughout the day, it will discharge faster. And it turns out once it discharges fully, the voltage is about 3 volts or something. Now it turns out all your circuits, that is all the chips that are manufactured, they will be designed so that even if the power supply varies by, let us say, plus or minus 10%, the functionality is fine. Beyond that, you can't guarantee. Right? So which means if you directly rely on your battery voltage to generate all these supplies, that is not a great use, because you see the discharge rate is so much and you can tolerate only 10% change. So if you just rely on the battery, and use to generate the supply voltages, that will not work, because then you can't tell the customer that your electronic system will work only if it's 100% charged. Even if it's 90% charged, it will not work, because then you have to carry a transformer along with your phone to continuously keep charging. That's not a practical thing. So which means you can't just use a battery for this. There will be some block on chip that will actually go and generate all these supply voltages, and of course this block will be powered by the battery. Right? Now let us say I want to generate this supply 1.2 volt. I want to make sure that it is exactly 1.2 volt without any error. Now based on whatever you have learned so far in all your analog courses or any course, if I want to make one quantity exactly equal to something without any error, what might be the general principle you will use? Some kind of negative feedback system, right? And how does a negative feedback work? If you were to explain in English, how does a negative feedback work? What does it do? Yeah, essentially you first sense the output, right? And you compare the output or a scaled version of the input, scaled version of the output with some other quantity, and that can be an input signal or a reference signal, right? So which means for this negative feedback system to work, you need some block which generates a reference voltage that can be used for comparison. And let me call this on-chip reference. Of course, this will also be powered by the battery, right? Or some, let's say, yeah, something. Let's say it's not very good. So this is how typical power generation is done, and this block is what we call as voltage regulator, if you have heard of this term before. So we'll look at both these. So we'll look at how to generate on-chip references, and we'll briefly see about voltage regulators in the rest of the course. So first let's start with how to make on-chip reference. So the goal of this on-chip reference is to generate an voltage which remains constant irrespective of any variations in your process voltage or temperature. So which means irrespective of what happens in the outside world, its job is to provide a voltage which is constant. If that is the case, if I try to sketch the IV characteristic of such a reference voltage, so voltage is in the x-axis, current in the y-axis, how will the IV characteristic look like? Straight vertical line. Voltage is constant irrespective of the current. Right? But of course, this is the IV characteristic of what element? Yeah, ideal voltage source. If you have an ideal voltage source on chip, you don't have to do anything, but unfortunately it can't do it because voltage source is a active device, it generates power. On chip we can only have elements that can dissipate power, so we can have only passive devices, right? So if you know that we can only make passive devices on chip, is there any comment you can make on the IV characteristic of passive devices? If I have a passive device and I sketch its IV characteristic, is there any particular property or comment you can make? Okay, so let's say finite slope. Okay, that's okay, fine. Is there something else more fundamental? Okay, let's say this is some device. The typical convention we follow is if the current is in this polarity, we define the voltage in this polarity. And passive devices generate power or dissipate power? Dissipate power. What is the power dissipated in this device? V times I. So if this were a passive device, what can you say about this power? Greater than 0 or less than 0? Power dissipated is positive, so it's greater than 0. If you know this information, now can you make any comment on the IV characteristic? It should lie either on the first or third quadrant, right? So which means I cannot have a voltage reference which has a characteristic like this because it's now entering the fourth quadrant. So what should this characteristic do? If we have to, we can only have passive device. We just told passive devices can have characteristic only in these two quadrants. So which means my characteristic cannot do this and enter the fourth quadrant. What should it do? Yeah, so it has to enter my third quadrant. So what is one point in the characteristic I will definitely pass through? Origin. Something like this. This is a more realistic thing that you can have on chip. Right? And do you know any element that has this kind of characteristic? A diode. And as you see, diode should be forward biased or reverse biased. Forward biased, you can see if diode is forward biased and you make sure sufficient current is getting pumped into the diode, the voltage sort of remains constant. So let's see how we can make it. So I have a diode. So how I want to get this voltage. So how can I get this voltage from the diode now? What do I do? What can be done? You can add a current source, right? And I just have to make sure the current has at least this much of value, right? Beyond some particular current, you see that the voltage sort of is constant. So let's say I call this I1, I call this the diode voltage VD. And if this is silicon diode, what is the diode voltage approximately? Yeah, 0.6, 0.7, let's call it somewhere here. So let's take a middle ground and say it's 0.65 volt. So this is something we can do. So let me take it to the next page. What is the IV relation for a diode? Let's try to get it mathematically. If I have, what is the IV relation for a diode? ISC power? Yeah, VD by VT, actually -1 to be exact. Yeah, because for 0 voltage the current should be 0, so you need to have -1. So which means what is the diode voltage in terms of the current? From this, can you tell me what is it? Vt ln of 1 plus I1 by Is. Is that okay? And this we can further approximate for all practical purposes Vt ln I1 by Is. And the characteristic is this. I'll draw it here maybe. Okay. So as we clearly see, even if I go and change the current by a large factor, the corresponding voltage is changing not by so much. So it's a decent reference. And you can also look at it from the equations also. The current is actually getting passed through a log function. Log is a compressive function or expansive function? Compressive. So which means even if there is a lot of change in the current I1, that is sort of compressed by this function. So the voltage does not change. So now one quick digression. So it turns out in many CMOS processes, it is not possible to get an isolated diode because of the following reason. So remember, we all have in CMOS process we have a common P substrate, right? And typically, where is this common P substrate connected to? Where do we connect the substrate to? Remember, this is the body terminal of all NMOS transistors. Where do we connect it to? We connect it to ground. Now if you want to make a PN junction, so this is V, so this is P. So to get a PN junction, you might want to make something end like this. So and we expect that we have gotten a diode this way. But will this diode be fine, or we can't use this diode? Can we use this diode for our purpose, or we can't use? It won't be forward bias, so we can't use it. So which means this alone is not sufficient. So which means the issue is because the P is kind of rounded, right? So N is fine. So what do you suggest we do? I have a N junction, N region. I want to get a PN junction. So what can we do? We can try to put one more P. And you can get, now you can get a proper, and now we can try to use this PN junction as the diode. But as you see, unfortunately, you don't get that diode alone isolated. You also have the bottom diode. And this is basically ground. So which means now you no longer have one PN structure. We have a PNP structure. You can connect N to ground, but that will not solve the problem of this, right? Okay, when I just had this P and N, what was the problem? I had this diode, but correct. So now you see we have a P and P structure like this. So do you guys know what this is forming? It turns out this forms a bipolar junction transistor, or a BJT. It's another kind of transistor if you don't know. Or to oversimplify things, this is grandfather of MOSFET. That's all. Okay. And yeah, this is, let us say, the symbol like this. Same thing as this. We'll call it emitter-based collector. It's not important. So now you see we have three terminals like this. But among this, do I want the top diode or the bottom diode? Top diode. So if I want to have only the top diode, where can I connect this base terminal to? If I connect this to ground, then you see that the other diode is completely out of the picture. Now we can nicely use this as a forward bias diode. So which means here correspondingly this terminal is grounded. I mean, same you do here also. And in fact, this is how the name diode connection came. I mean, because remember, if we have a MOSFET like this, so we typically call this diode connected structure, right? And that came because when we did the same thing with BJT, when you shorted base and collector, essentially you are kind of bypassing this diode, you end up with a single diode. So that's why this was called diode connected, that name kind of stuck. So anyways, the point I want to make is the following. In most processes, you can't get an isolated PN junction diode. You end up with a parasitic bipolar junction transistor like this. Okay? So you don't, so essentially this is not a true diode, it is a BJT which is diode connected. That's all. So which means, let me take this to the next page. I'll still draw it as a diode for simplicity, but I'll call this voltage as VEB because the diode we are getting is between emitter and base, VEB. So to explicitly show that this is not a true diode, it is a diode connected transistor, I'll mark this voltage as VEB. Let's say this is VEB1. And we already know VEB1 is VT ln of I1 by IS. And what is VT? What is VT here? KT by Q. K is Boltzmann constant. No, T is temperature in Kelvin. Q is the electronic charge. Good. So now this is a very good starting point to get a voltage reference on chip. But let us say, let me see if we can, yeah. But let's say I try to do this experiment and measure this voltage. Let us say in the campus I do this experiment once in the month of December or January where temperature is very low, and I do the measure this voltage again in the month of July where it's very hot. You think this voltage will be constant with temperature, or will it change with temperature? Will it change? How will it change? Will it increase or reduce? What do you guess? This is the equation. As I increase temperature, what do you expect will happen to the voltage? Huh? Why? Because of this temperature T, we suspect it increases, but it turns out this IS has a strong dependence on temperature, and because of this, if you actually try to measure the voltage as a function of temperature, you actually see that it sort of groups this way. And if you try to approximate it as a linear curve like this, this slope roughly is about minus 1.5 millivolts to minus 2 millivolts per Kelvin. This roughly. And this kind of behavior is often referred to as complementary to absolute temperature. In short, CTAT. Okay, so which means now this voltage was a decent starting point, but it looks like if I keep changing the temperature, this is not remaining really constant. So let me move to the next page maybe. It's a name complementary to absolute temperature. It means that as you increase temperature, it is behaving in a complementary fashion. Increase one quantity, the other quantity reduces. Just a jargon. So I'll erase this. Let me see. Yeah. So let us say this is the voltage you have right now. But finally, for your voltage reference, as an increased temperature, what do you want that reference to look like? Huh? I mean, for your voltage reference, if I increase temperature, how should it look like? should remain constant. So let us say it should do something like this. Constant. Now tell me I have some quantity which is reducing with temperature. I want to get a final quantity that should be constant with temperature. What do you think I can do in English? If I have some other quantity that sort of increases with temperature, and if I sort of try to match the slopes of these two and add up in an appropriate fashion, hopefully I'll get a constant voltage. Okay, that's the idea. And if you have any quantity that increases with temperature, and in particular if it's increasing linearly with temperature, it is called as proportional to absolute temperature for obvious reasons. Also called as PTAT. Okay. So now our job is to try to generate some quantity or some voltage which has a direct proportionality to temperature, right? So now let's start with what we have right now. So we have this single voltage as kT by Q, ln of I1 by Is. So here you see that this temperature T gives a nice proportionality constant, nice proportional behavior to temperature. But what is resulting in the complementary behavior finally? What this term Is. If I don't have this term Is, I am set, right? So mathematically, what should I do here so that Is goes off? If I give you option to change the argument inside, what will you do here so that Is cancels? You multiply by Is. Let me say write it here. But of course, we can't multiply by Is alone because dimensionally it will not be consistent. So what should you do? If I just multiply by Is, you have a quantity that is that has units of current. Argument to a log function should be dimensionless. So what should you do now to make it dimensionally consistent? Divide by some other current, let's call it I2. And I should make sure this current I2 does not vary with temperature, right? So let us say I have another current I2, then Is cancels. So now use your math preparation for JE and expand it, kT by Q. How can I say this? I1 by Is. And how can I write the second term as in a more practical format? Plus kT by Q, or minus kT by Q. Yeah, this is a more relatable format. Fine. So now if I generate a voltage which looks like this, that we know will have a PTAT behavior. Okay. So let's see how we can do it. So do you know how to generate this voltage? That's something we already have. How can we generate this second term of the voltage? What should I do? To get this voltage, what did we do? We passed a current I1 through a diode. Now I want to get this voltage, so what should I do? I should pass a current I2 through. I have a current I2. What do I do to this current? I should pass through another identical diode. So let me call this VEB2. If I take the difference between these two, that gives me this. So this is essentially kT by Q. If I simplify it, ln of I1 by I2. And let's say I choose, I can always write I2 as some I1 by N. So then what will this simplify to? I1 by I2. I1 by I2 becomes N. So this becomes kT by Q into natural log of N. Now we can clearly see this is a constant. So we have a nice linear dependence to temperature. Hmm. We call this VEB1, VEB2, and I'm now trying to take the difference. So now typically, as you know, it is easier to actually copy and mirror currents. So let us say I don't want this to be I1 by N. I want to scale it to I1, right? So which means I'm putting N copies of this current source in parallel, and I make it equal to I1. Which means if this voltage should not change, what should I do here? I'm putting N current sources of this in parallel. I don't want to disturb this voltage, so what should I do here also? What should I do here? I mean, remember, how did we scale circuits? I mean, see, if I put two identical circuits in parallel, will the voltage change? I don't want to change this voltage, but I'm saying I'm putting N current sources in parallel. So which means to keep this voltage same, what should I do here? I should put N diodes in parallel. So I'll call this saying a diode, you have one diode, here I have N diodes. So which means I can say that this current is equal to I1. I mean, that way it's easier to, if I have current I1, I can easily copy and mirror the current using current mirror. That's why. So now this is also I1. So now what we have established is, if I have a single diode voltage that has a PTAT behavior, if I have a voltage obtained as difference of two diodes, I'll call it delta VEB, which is essentially VEB1 minus VEB2, that has a PTAT behavior. So now to get a constant voltage, what should I do? I should add these two with a proper scaling factor so that the slopes of the two curves exactly cancel. So let's see what we can do. Let me take it to the next page. So the PTAT voltage is KT by Q ln of. So which means now I need to get my output as the PTAT voltage, I'll call it VEB1 plus a scaling factor Kp times the PTAT voltage, which is VEB1 minus VEB2. So that is essentially VEB1 plus Kp times KT by Q ln. Okay. Now how will I choose this, how will I find this value of Kp? I mean, why do I need this scaling factor Kp here? To match the slopes. So which means, how do I find this Kp now? I mean, you told you wanted this factor Kp so that the slopes of the PTAT and PTAT match. So how will I find this Kp now? Differentiate what with what? I differentiate the output with temperature. Now I know this is my PTAT voltage. Let us say from simulations or from measurements you can find what is the slope. So let's say, for example, it is minus 1.55 millivolts per Kelvin. Plus I take the first derivative of this with respect to temperature. What do I get? Yeah, Kp times K by Q. And this K by Q will I'll write it as KT by Q by T. So which means I'll replace it with the thermal voltage Vt. This is a convenient way to write it because, I mean, at room temperature of 300 Kelvin, what is the thermal voltage? 25-26 millivolt. So which means I can find the slope directly by putting 26 millivolt and 300 here, right? Otherwise, you have to find, I mean, divide K and Q. This is probably difficult to do, right? That's all. And if I differentiate it, what should this be equal to? What should the slope be? I mean, what should the derivative be equal to? You want this to be equal to 0. So which means from here you can directly find Kp times Vt ln of n, that is T times 1.55 millivolts per Kelvin. So at room temperature it is 300 times whatever. So how much does it come out as? 3 times 1.55, 465. And so which means I know this factor. Let me see. So which means I now know Kp times Vt ln n to be this much. Kp times Vt ln n. Sorry. This is Kp times Vt ln n. This is 0.465 volt. And what is VEB1 approximately? How much is this voltage approximately? 0.6, 0.7, let's say 0.65. So if I sum up these two, what do I get? Right, so roughly, so the output voltage you get here finally will be approximately about 1.12 volt. And if you have taken any courses on semiconductor devices, has anyone taken a course on devices here? Yeah, so what if you hear this number 1.12 volt, what does it remind you of? It turns out this is a band gap of silicon semiconductor. Band gap is an intrinsic property of semiconductor, and it turns out if you do all this and get a constant voltage reference, that turns out to be the band gap of silicon. And it's not a coincidence. If you actually take all equations and work out, you can actually show that this is equal to the band gap voltage, but that's not relevant. So because of this, this circuit is called as band gap reference. So voltage reference, and it turns out that voltage value is equal to the band gap of silicon, so we call it band gap reference. Cool. So still we have only talked in English, we have not looked at the actual circuit. So let's actually try to implement in circuit. Let me erase all this. Yeah, so all I need to do is the following. I have to generate my output as VEB1 plus Kp times VEB1 minus VEB2, right? So the point to always remember is this: if I take one single diode voltage, it is complementary to absolute temperature. I take difference between two diode voltages, that is proportional to absolute temperature. All we are doing is adding these two by scaling one term, that's all. So now let's see how we can implement in circuit. So let me simplify this. So I have VEB1 times 1 plus Kp minus VEB2 times Kp. Now looks like I have two voltages, VEB1, VEB2. I need to scale one quantity by 1 plus a gain, another by minus some gain. So do you know some circuit that can give you a gain of 1 plus something and minus something? A gain should be minus k and 1 plus k. Do you know some circuit that op amp using? Op amp, correct, but op amp alone I can't use. What should I use the op amp as? Inverting and non-inverting amplifiers, right? So which means, let us say first I take the first term, I have EEB1. So this should be inverting or non-inverting. I use it as a non-inverting amplifier, so I take this op amp. I call this R2, R1, So what will be V out now? VEB 1 times 1 plus R2 by R. Okay. So that gives me the first part. Now I also need to get this part. So what do I do? I mean, I have another voltage VEB2 that needs to be multiplied by minus some K. I should use it as what configuration? Inverting. So what can I change here to get this directly? Huh? Okay, terminals. What should I do exactly? Apply at the negative side. So if I connect here, connect this point to VEB2. Now we can use superposition. When VEB2 was not there, this is the output I got. Now VEB1 is not there, only VEB2 is there. What will be the voltage I get? Minus R2 by R1 times. So this way, in a single circuit, you can get this full operation beautifully done. So what is the gain Kp here now? What is determining this? Now tell me this, right? So we want to essentially do this thing so that we get some quantity that is independent of temperature. But I assume that this gain is constant Kp, right? But now I have Kp as R2 by R1. Do you think this gain will change with temperature or will it not change with temperature? Why? Yeah, resistance value will change with temperature. But here the gain depends on the absolute value of resistor or something else. Ratio of two resistors. So which means if you make both resistors using similar kind of elements, with temperature change, let us say R2 becomes R2 into 1 plus delta. What do you think will happen to R1? That will also change by the same factor. So which means ratio will be constant. So it again boils down to the fact that on chip you can have a small random mismatch provided you size elements to be large enough, and the ratio will be tightly controlled. Just that there is going to be process variation, which means the exact value of R2, R1 will not be known to you, but both of them will have the same value. Right? Process variation is there that you can't do a lot, but the random mismatch you can nicely control. I mean, relative mismatch is like this, right? I mean, it's like relative grading. So it doesn't matter if you didn't do an exam well in the class, as long as everyone in the class also is not doing it good. Same thing. So that's it. So now we can put all together and form the complete circuit. So let's do that and see what happens. So let me see if I can erase this. So I'll just take this now. So let's see if I can mark it directly here. Okay, so let me draw this here directly. So I should connect VEB2 here. So this is VEB2. I'll directly go and connect it here. Similarly, VEB1 I'll connect to the left side. So let me do that. So this is VEB1, this is VEB2. So this is also VEB1. So which means, what can you say about this voltage? If this is VEB1, what can you say about this voltage? And now we can say that this is my output. But before proceeding further, Look at the circuit and tell me what is the current flowing on the left side branch here, left side diode. What is the current flowing through the diode? I1. Ideally, what do you want the current flowing in the right side diode to be? No, I1. I mean, ideally, what did you want here? What did you want the current here to be? I1. So, but here, what is the current that is flowing through the diode? Can you tell me? Is it I1 or something else? Yeah, why something else? I mean, what is the current flowing in this branch? That's what I'm asking, right? Is it I1 or something else? Yeah, I mean, let's say if I, is it clear that this current is not I1? So I have current I1 plus some other current flowing this way, correct? And remember, the current flowing here and here are same. So what is the current flowing in this direction? Through R2, what is the current flowing? No. What is the current? I mean, current flowing through R2 in terms of the voltage and current. Tell me. I mean, what is the potential difference across R2? No. Okay, what is the potential difference across R2? R2, right? So the current flowing here is I1 plus this much. Right? Is this what you wanted or not what you wanted? Not what you wanted. So what is the solution to this? What can we do to correct this? What capacitor? No, this is everything is DC, right? I1 itself is DC. I mean, you passing. I mean, remember you are trying to get a voltage, constant voltage as a reference voltage, right? So everything is DC. You can't block DC currents and say I'm done. Then no current to flow. I mean, what is one trivial solution you can do? I mean, yeah, I mean, you can change the current source, right? That's the simplest solution. But of course, that is not really practical because you will not exactly know what this extra current is. And even if you know, you will not be able to go and change it to be of that value exactly. I mean, even here I can't ensure that this current is exactly I1. But I can ensure that these two currents are equal. Right? Again, I can match two elements, but I can't ensure that the exact value of that element is something. All I can say is the currents in these two current sources are equal, but the actual current can be different than I1. So if that is the case, instead of changing the value of the current source, if I can do something to make sure the additional current is getting pumped here, I am set. Correct? If I somehow add an additional current, that flows in this branch, here, okay? Now I need to generate a voltage which is Vout minus VEB1 by R2. I have Vout here, I have VEB1 here. What can I do? If I go and put a resistor R2 here now, what will be the current flowing? Same thing, the Vout minus VEB1 by R2, and that current is flowing here, and that will actually act this. Next.
Vout is set by the name of the.
Yeah, correct.
Aren't we trying making Vout to be equal to VEB1?
Is that what you want? Your Vout, you want it to be something else. What did you want your output for? You want to get some voltage that is constant, right? Yeah, you want to keep this current to be 0, right? That's a trivial solution, but that's not what you want. So this will definitely work, and this is one implementation of bandgap reference. But here let's actually try to see if we can do some further simplification. Now tell me, let's see if everything here is required, or you can get rid of some unnecessary or redundant elements. Let me remove some clutter here. So tell me, do I need the diodes in the circuit first? Do I need the diodes or not? I need the diodes. Okay. Do I need the op amp? we needed the op amp to get the gain. Same with R2, R1. R2, R1 was setting the gain. And this R2 is making sure the currents are equal. And what is the current flowing here? I removed it. It is I1 plus Vout minus VEB1 by R2. What is the role of the current sources here? What were they used for? Yeah, to provide some current so that the diode is forward biased. Now the current flowing through the diode, is it I1 or something else? Something else. So is there some simple choice you can do for I1? Even if you make I1 to be 0, the circuit will work, because you have some current getting pushed by the op amp through this way. Is it correct? I mean, the whole point of having this current I1 was to make sure some current is flowing through this diode so that it is forward biased. So now I no longer need it. Even if you have it, it's okay, but it's just redundant. So we can simplify it this way. So this is one variant of bandgap reference. So I'll redraw this in a way that you might find in textbooks. I'll actually copy paste it. Keep it here for reference. So first let me draw the diodes. So I have one diode. I have n diodes. So this is here. And through the n diodes I have a resistor R1 connected. So I'll draw that here. And then other end of R1 is connected to the inverting terminal. So I'll draw the op amp here. And then I have R2 here and R2. So this is going to be the final Vout. So this is VEB1, VEB2. Right? Huh. Vout has not changed? Yeah, I mean, see, the entire calculation for Vout made the assumption that the diode drop is roughly 0.65, and that is guaranteed as long as sufficient current flows through the diode. For example, now the current flowing through the diodes is Vout minus VEB by R, right? I know my Vout is roughly 1.12 volts ideally. VEB is 0.65 volts, let's say 0.6 volts by R. So this is about 0.6 by R. So if you choose a reasonable value for R, you will have sufficiently large current flowing through the diode. I mean, diode voltage doesn't depend on the current. That's the whole premise, right? As long as sufficient current flows through the diode, I am set. Okay, so now tell me this. So do you think the op amp in the circuit, let me erase this. Do you think the op amp has only negative feedback or positive feedback here? Look at the circuit. Do you think it has only negative feedback or it also has positive feedback? Huh? Because you see that the output is fed both to the inverting and to the non-inverting terminals. So do you think this is a good thing or a bad thing? Finally, what do you want in your circuit? For op amp, do you want at DC you want negative feedback or positive feedback? For op amps, remember always you should have DC negative feedback. Only then all the bias points will be defined properly, transistors will be in saturation, and op amp behaves like an op amp. But here I see that I have both negative and positive feedback. So what should be ensured in that case? I mean, you are earning every month, but some expenditure is also there. At the end of the day, you should save something. So what should be the equation? Yeah, you should earn more than what you spend. Similarly, so the negative feedback should dominate the positive feedback. That's all. So let's see if that happens. So as usual, I'll break a loop here. So let us say this voltage here increases. Voltage increases. So these two voltages will increase or reduce? Increase. Now I just have to find which of them increases more than the other, right? Now tell me I increase, let's say I make a delta V change to this point. How much do you think the change here will be, change on the right side will be greater or the left side will be greater? Looking, we are all looking at small signals. I am making a small signal change delta V. Approximately what will be the change that you see here? This increases by delta V. How much will be the change you see here? Approximately. Huh? Why? What about the diode? When the diode is forward biased, what can you, for small signals, how can you replace it as? Huh? A resistor, some small resistor, right? So let's call it some RD, and you have n diodes in parallel, so it's, let's say, RD by n. So here the change will be delta V times R1 plus RD by n by R1 plus R2 plus RD by n. What will be the change you see here? Delta V times how much? RD by? Okay. So which of the two is higher now, left side or right side? I mean, diode resistance, is it small or very large? It's going to be really small. So then tell me if the left side is higher or right side is higher? I have two things, right? Right side is higher. So this will increase more than the left side. Is that okay? I mean, assume that diode is even short, right, for simplicity. Right? So then do you think we have strong negative feedback or positive feedback now? I increase this fellow, my inverting terminal increases more than the non-inverting terminal. So which means the output of the op amp, will it increase or reduce? My inverting terminal increases more than the non-inverting terminal. So the output will, so which means we have negative. So but yeah, so anytime you have case like this where you have both negative and positive, you try to make sure that the negative feedback dominates, especially at DC. That is very crucial. So the way we derive the circuit, you don't have to worry because the signs came organically, but otherwise you should have this. So let's try.